In order to give you a variety of examples that you can use to work through and see the solutions for, I've generated four problems for you guys today. The first problem being a simple energy problem, so no work has to be accounted for. It's a simple conversion of energy problem. The second one, a similar problem, however, now there's, I believe, friction, and therefore there's some work that's performed. So energy will either leave or be entered into this system. The third problem is an example of how using work and energy can determine the force that acts on an object. And problem four is just using work to analyze like changes in energy and just using the concept of work to see what effect the total energy of the system, how that total energy has changed. So let's get right to an example. So the first one is one of your simple um, energy calculations. So I have a ball that's being held 5 meters above the ground. It has a mass of 2 kilograms. After I let go of it, it begins to fall. It's fallen 3 meters, so it's 2 meters from the ground. And simple question: how fast will the ball travel when it is 2 meters above the ground? So it's at rest here. Once I let go of it, once it's fallen 3 meters, how fast is that ball traveling? Please notice as I go through these examples that the approach to every problem is exactly the same. And that's what's nice about these conservation of energy problems. The setup is exactly the same. You just have to try and understand whether or not work has actually been performed. So here, my total energy is before, my gravitational potential, my kinetic, and my elastic potential must equal those same energies afterwards, the total of. At this location, I have height, so I have gravitational potential, but I have no velocity, no spring, so these two are not present. They're zero in the initial stage. After I let go, I have some height, so I have gravitational potential, definitely have velocity, so I have kinetic, still no spring, so I don't have to account for any elastic potential energy. So as you can see, all I'm left with is initially I had all gravitational potential. Afterwards, I have a combination of gravitational potential as well as kinetic. If I plug in the equations for each of these, I have mgh before equals mgh plus 1 half mv squared afterwards. These are based on my final values. These are based on my initial. So my mass is 2. My height is 5 for the initial case. For the final case, my mass is still 2. However, this time my height is only 2 because it's dropped 3 meters. Plus 1 half mv squared. So everything I had in the beginning that was gravitational potential is converted to a lower amount of gravitational potential. Since I've lost some of this, I must have gained kinetic. If I just solve this through, you will find that that ball must be traveling at roughly 7.67 meters per second. Just realize all your energy before must equal all of your energy afterwards. Second example, now we have some friction. You can tell because this block is slowing down. It goes from 10 meters per second to 3, and it has a mass of 8 kilograms. Additionally, the question being asked is how much work has been performed? Well, in order to have work be performed, you have to have a force acting over a certain distance. So clearly there's some kind of force at play here. So work is being performed. Same setup as before. The total of my three mechanical energies before has to equal the total of my three mechanical energies afterwards. No height and no spring before, no height and no spring afterwards. Since I do have some velocity in each case, I will certainly have some kinetic energy. So the kinetic energy I have here before must equal the kinetic energy afterwards. If we plug our values in, 1 half mv squared before must equal 1 half mv squared afterwards. The difference is I'm going at 10 meters per second before and only 3 meters per second afterwards. So what you'll notice here is this side equals 400 and this side only equals 36. Ignore this for 1 second. 400 certainly does not equal 36. So we know that since these are not equal, work must have been performed. Energy has left this system. I originally had 400. I've lost enough to knock me down to 36. That energy had to have gone into some other non-mechanical form. Sound, heat, light, something along those lines. So I'm going to add plus work here anytime I see that these values are not equal. If they're equal, no work's been performed. They are very clearly not equal here, so I have to account for the work, the energy that left the system. If I subtract 36 from each side, I get 364 equals the work. It's a negative work because I've lost that energy. You can see I had 400, then I had 36. So the work that was performed was negative 364 joules. Because remember, work is a change in energy, and I've lost 364 joules from when I began to when I ended. Same exact setup, just the added step of realizing these are not equal, so I must account for work. Third problem, a little bit more difficult, but the same setup. I have a crate that's moving on a frictionless part of this surface over here, mass of 12 kilograms, velocity of 15 meters per second. It's going to slide onto this frictional surface. Hopefully you realize by now that that friction will perform work. It will steal energy from that block and convert it to most likely heat, probably a little bit of sound, both forms of dissipated energy. So the question being, once the crate slides onto this frictional surface, how far will it travel if the force of friction resisting the crate's motion is 25 newtons? So if the friction pushes the block to the left with 25 newtons of force, how far will this block travel? So basically, how long will it take for that frictional force to convert all of that mechanical energy into something like heat? Well, just like before, we will look at our before case and our after case. I have no height and no spring, so before I only have the kinetic energy. Afterwards, I have no height, no velocity, and no spring, so I have 0 afterwards. As you can see, EK cannot equal 0. Now this just means I have no mechanical energy left, so it must have left the system through work, so I will tack on the plus W. What this tells me is that the kinetic energy I had before, 1/2 mv squared, must equal all that work that was performed, all that energy that left the system as heat and sound. Plug in the values I know, and I can find that the work performed was negative 675 joules. I had 675 joules of kinetic energy initially. I lost all that mechanical energy, so I must have produced 675 joules of heat energy, sound energy, etc. We have to go one step further here. It is a slightly more difficult problem. Work is not only a change in energy, it is also the force times a displacement times the cosine of the angle between the force and the displacement. So I want to quickly show you this diagram over here and show you that the box is sliding to the right. It's being displaced to the right. The force of friction is resisting that motion to the left. The angle between these two is 180 degrees. So I'll take my work, I'll plug in my force of 25 newtons, and I don't know my displacement, but I know the cosine of 180 degrees is my final term. I'll simply solve for my displacement and find that in order to bring this crate to rest and steal, so to say, all of its energy, to convert all of its energy to heat and sound, it must slide for a total of 27 meters. Again, just like to highlight the same process, one added step of taking the work I've calculated at the end and just relating it to the other equation we have to find the total displacement. Last problem, problem number 4. We have a crate with a mass of 80 kilograms, no velocity. This guy comes along, gives it a push. If he pushes it for a distance of 10 meters using an applied force of 40 newtons, how fast will the crate be traveling at the end of that push? Well, again, hopefully you realize since you see a distance and a force, we're going to be dealing with some work here. But in case you didn't, I have no energy before, no height, no velocity, no spring. And afterwards, I have no height and no spring, but I am moving. I certainly have some kind of kinetic energy. I didn't mention it. We're going to assume these are frictionless surfaces. That will complicate things if we don't. So before I start with nothing, I magically gain some kinetic energy. Again, this doesn't really violate the law of conservation of energy. It just says I had no mechanical energy to begin with, and I gained a whole bunch of kinetic. This guy over here has a bunch of chemical energy in his body. So by pushing that, he converts it. He technically burns calories. So he burns his chemical energy, and that's where this energy comes from. So he feels a little bit more tired afterwards, and this thing is now moving faster. It's taken some of that chemical energy, and it's been converted into kinetic. This is a sure tell sign here that work was performed. So I'm going to add it on this side over here. So I didn't start with any energy, but that man performed some work, and that has to equal the kinetic energy I gained. Now we know work is force times displacement times the cosine of the angle between the force and displacement, and that in this case will have to equal 1/2 mv squared using the final velocity. I drew a quick diagram here to show you that the displacement is to the right and the force from the man is to the right. If I overlay these on top of one another, I get an angle of 0. There's no angle between these two. So the force I was given in the problem, 40 newtons, times the total displacement, which was 10 meters, times the cosine of 0 must equal 1/2 times the mass, which is 80, times the velocity squared. These numbers, 40, 10, and 80, all came from up here. 80, 10, 40. They were all taken from the problem. Once I do that, I simply just have to solve for velocity, and I find that that final velocity after that 10-meter push using 40 newtons will produce 3.16 meters per second of velocity. These were a variety of different problems. Hopefully, what I'd really like you to see is that each of these problems is solved exactly the same way, looking at the before and the after. And the only real determination you'll have to make, either conceptually or mathematically, is whether or not you have to add on the work that was added or the work that was removed. And that all comes down to whether the energies are already equal or some of it left to the system, or in a case like this, some of it, oops, where you go? I apologize. Or in a case like this, some of it was added initially, and then that's what produced the energy at the end. So just be really careful and just realize that each of these is the same approach. If your bookkeeping is very good, these problems tend to be very, very easy. If you're not as neat as you could be, you may tend to run into some problems. So please just make sure you start with the same process and be really careful with the energies that you're considering.